In the fading light of a September evening in 1992, high in the Colorado Rockies, a small team of engineers stood on the edge of history. Before them lay 6 Mile Lane, a nearly flat stretch of highway framed by towering peaks and crisp mountain air. The scene was serene, but for James Osborne, John Garbarino, Kevin France, and writer Chris Huber, the pressure was anything but calm. After 5 years of relentless work, sleepless nights, and countless setbacks, this was their final chance to break the world speed record for a human-powered vehicle. The stakes were high. They had secured sponsorship, poured every resource into their dream, and built a machine so precise that it was a true marvel of modern engineering. Yet success depended on a perfect union between man and machine, with every variable from weather conditions to the rider's physical performance having to align. The CHEETAH, their custom-designed semi-recumbent bicycle, had the potential to change everything. Breaking the record would not only validate years of effort, but also solidify their achievement as a defining moment in the world of speed and innovation, one that would be remembered for generations. But how did this journey begin? To understand the true weight of this moment, we must go back to where it all started. On a college campus at the University of California, Berkeley, where a group of young, idealistic students dared to dream of making the impossible a reality.
My name is James Osborne, and I was one of the co-designers and one of the key team members on the Cal HPV team. I was in the class of 1989 at Berkeley.
My name's John Garbarino. I graduated from the University of California, Berkeley in 1989. And at one point, I was the director of the human-powered vehicle team there. But to say that that was my only role, I think we had a lot of roles because you had to be kind of a jack of all trades to be in the HPV team. You designed and you built and a lot of collaboration.
I'm Kevin Franz, and I graduated in 1990. Played a bigger part in trying to get sponsors and trying to get material and equipment.
I grew up and went to school in Southern California, and I took a high school aptitude exam that basically told me I should be a mechanical engineer. I ended up applying to a number of schools, and I got into UC Berkeley, and I came to college, and I never left. I'm still here in Berkeley.
You know, there's a lot in the Berkeley reputation being the number one public university, and particularly in engineering at that point. And the proximity to where I lived, which was about 30 minutes away, made it somewhat of a no-brainer for me to go to one of the best public universities in the United States.
At Berkeley, in the Cal HPV team, we competed in the ASME competition, and that's the American Society of Mechanical Engineers. It's an association of mechanical engineers across the country, and they sponsor collegiate competitions. Many colleges participate, and we were one of them.
One of the reasons I went to UC Berkeley was because the ASME program was strong.
The American Society of Mechanical Engineers, or ASME, is a professional organization dedicated to advancing engineering knowledge and innovation. Every year, it hosts the Human-Powered Vehicle Competition as a way to encourage students to apply their engineering skills and creativity in real-world scenarios. It was this very competition that brought our team together and became the platform for their ambitious project. But what exactly is the Human-Powered Vehicle Competition?
You know, what was the human-powered vehicle competition was basically something that was a demonstration of mechanical engineering in all the disciplines of it, right? In terms of design, testing, and analysis. So it's an opportunity to demonstrate how well you mastered all those things.
We were trying to show that our mechanical engineering department was worthy of being ranked like in the top, probably 1 or 2, maybe top 5 in the country. So when we went to the competition, it was only just about, oh, our bike did well, but it was really representing our school to try to demonstrate that we were, superior or stronger mechanical engineers than the other schools on the West Coast.
To understand the human-powered vehicle competition, we first need to ask, what exactly is a human-powered vehicle?
A human-powered vehicle, or an HPV, is basically a vehicle which is streamlined, so it has some kind of aerodynamic shell or other means of making it more efficient than just a bicycle. Many of the early human-powered vehicles were tricycles.
So I grew up cycling. I grew up competitively cycling, and for me, aerodynamics was always, something I felt firsthand. And a human-powered vehicle basically is an individual using an airfoil that's around them fairing allowing them to optimize their own individual speed. And that's a lot different than a bicycle, and you can more than double your speed with the aerodynamic shell around you.
The human-powered vehicle competition was still in its early stages, with the first event taking place in 1983, just 3 years before James joined the Cal HPV team. Hosted at the University of California, Davis, the inaugural competition was won by Chico State. Yet, the excitement surrounding HPVs extended far beyond college campuses, fueling a growing movement in the engineering world.
When I got involved, it was 1986. It was right when there was a international competition, but it was really an award that DuPont Corporation sponsored for anybody, any team in the world. If they could break a 65 mile per hour speed barrier, there was a team that had just basically won that competition and got that prize.
It was Fast Freddie Markham who made history by winning the $18,000 DuPont prize in 1986. Riding a recumbent bicycle designed by Gardner Martin, he set a record-breaking speed of 65 miles per hour. That legendary bike, known as the Gold Rush, now resides in the Smithsonian Institution Museum of American History in Washington, D.C.
The guy that actually designed and built that vehicle, he had basically built the thing with no engineering education or strong engineering principles, just basically mechanical intuition. And he used an airplane wing that he basically cut out the middle section of and put it together and then faired it all together to create his fairing. Our impression at Berkeley in the team was that, we can do better than this. And so it became kind of a goal to try to break the world speed record.
When James joined the ASME team at Berkeley in 1986, the students had already built and competed with their first bike. A 3-wheeled tricycle made from a steel chromoly frame and covered with a styrofoam aerodynamic shell.
There had been one bike basically before I got involved, and they had some success. They didn't win or come in first in the collegiate competition, but they had generated a lot of excitement, and that was about the time that I got involved with the project for the vehicle after that.
At the time, mechanical engineers were fascinated by lightweight structures. Composite materials were considered the gold standard for making designs both strong and light. The team's second bike, Vitesse, French for speed, took this concept further, featuring a lightweight carbon fiber frame that pushed the boundaries of innovation.
So the second vehicle was also a tricycle. We did fairly well with that vehicle, but we did have a number of problems with it that encouraged us to move in a different direction. After that second vehicle, that was around the time that John joined the team, and we basically decided we were going to build a brand new vehicle, decided to go for a 2-wheeled vehicle.
For James, it was the growing excitement surrounding HPVs that sparked his interest in the ASME competition. For John, it was his mechanical background and a touch of sibling rivalry that brought him into the fold.
Growing up with a mechanical background, doing a lot of working on cars and mechanical things and taking things apart and putting them back together, got me interested in mechanical things. And then key turning point, I think, was I went to the competition that James was involved with, the TAS up in University at Nevada, Reno. And my brother was working on the project and had been for, I think, 2 years with Chico State University. And so I got a chance to observe the competition and what it was all about firsthand. And then with him pushing me and beating me, which I guess I should thank him for at this point because the results were very, very positive in my life, I got involved in doing the human-powered vehicle at Berkeley. And it was one of the best things I've ever done. So it certainly worked out.
For me, I transferred into Berkeley in the fall of '87, and immediately I knew I wanted to be involved in the HPV program. And John was actually the president of the ASME club. So he was recruiting engineers, and because of my cycling background and knowing that I wanted to do HPV, I immediately went to the meetings and to learn more about what the plan was. And the plans they laid out were pretty exciting, but obviously there was a lot of work. And that, along with the school load, it turned out to be a lot of work that first year. In fact, it was a little bit distracting from school. And that was probably problematic for all of us because it was a lot easier and a lot more fun to go work on a bike project than it was to do your thermodynamics homework.
As engineers, you tend to be kind of the stereotype is a little nerdy into yourself, and that's an opportunity to be involved in something that you branch out a little bit. you take a little risk, and you definitely weigh your academic performance against having fun with this project.
In the 80s, it was a lot different than today. There was no, really, I had a Macintosh, James had a Macintosh, John didn't even own a computer. So it was a lot different time. There were no iPhones. You know, the actual phone in your house would ring, and John would say, hey, I'm going over to Echeverry Hall, and I'm going to be up on the roof starting at 2 o'clock in the afternoon. So you actually would inform your friends of the time, and it was kind of like you would call, you know, John would probably call 5 or 6 people and ask them to call 2 or 3 more people. It was kind of, that was the technology at the time. And we'd go and meet up on the hall and talk about what the direction is that we're working on. We would miss football games on this, and we would go up and work on the HPV instead. And we could hear the screams from the football game from the roof, but we were more interested in trying to prove our engineering prowess.
Being an engineering student at the time was incredibly exciting. In 1984, the Macintosh revolutionized computing, introducing the first successful mass-market all-in-one desktop with a graphical user interface, built-in screen, and mouse. It transformed the way engineers and students approach design and problem-solving.
So I'm going to paint a picture. You know, we're at the University of California, Berkeley, and honestly, people that I met there were the smartest people I've ever met in my life. You didn't go to Berkeley because you were just kind of like average. You went there because you were exceptional. James had the ability to do like 3-dimensional modeling on a Macintosh. To this day, I'm still in awe of his ability to write code to do that. But the thing that was really, that I remember the most, I'm sitting in a fluid dynamics class, and, you know, we had these brilliant professors that have written books and everything. And we were talking about, you know, the drag coefficient of different objects, whether it be a sphere or a square. And I raised my hand and I said, how do you design an airfoil? Like, how do you optimize and design an airfoil? And the professor looked at me like I was from outer space. And I said, we're working on a human-powered vehicle up on the roof of Echeverry, and we need to design, or we need to build airfoils. And again, he looked at me like I really knew nothing, or was just asking something. He did not know the answer. He didn't even know which direction to point us in. And so we actually then had to go discover things on our own. And at that time, you wanted to discover something, you would read maybe an article in a magazine, you get a name, or you make some phone calls. And it would take a long time. But to answer the question, how do we learn these things? We taught ourselves.
You know, really, we had a fundamental toolbox, which we were getting skills, analysis skills, design skills from our engineering curriculum. Right. And so what we were doing is being able to apply those skills. So there wasn't a class that told us how to design a human-powered vehicle. We had to synthesize all these, abilities and tools, statics, dynamics, and, other physics and aerodynamics, vibrations into this vehicle design. But we were putting the pieces together.
Through a combination of classroom learning and hands-on experience on the roof of Echeverry Hall, the Berkeley HPV team gained a broad and comprehensive education. However, their greatest lessons came not from textbooks or workshops, but from the competition itself.
The thing about the ASME competition is it's like the penultimate thing.
So the first year that I became involved, our idea was to make an aerodynamic shell that was as close to the ground as possible. It seemed like a great idea. We had a competition at Reno, and the speed portion of the competition, which is where you try to go fast in a straight line, was on a runway. But the result of this design choice was that it created this suction as the bike was going down the road. Dirt was basically sucked off of the asphalt into the wheel slots and just flung into the face of the rider. And I have this great picture of him where after he gets out of the bike, he's taken off his helmet, and his face is just black with dirt, and he's got black teeth from breathing the dirt.
After the competition in 1986, it became clear that the team would need to compete with a two-wheel bike, allowing the vehicle to ride further off the ground.
There were 2 competitions, Sacramento State and then Cal State Northridge. Those were in 1987 and 1988. But the anticipation leading up to it, you were getting everything prepared. And you show up and you have this vehicle that you unveil in front of all the other universities. People were checking out, what do they bring, what do they have?
The biggest part of going to these competitions was seeing everybody else's creation.
You would just basically go around and look at everything and take pictures and see, what were the interesting ideas that people had come up with.
And you showed up kind of trying to intimidate the other teams in the beginning. So it was a lot of fun because you show up and it was like being at the horse races. Everyone shows up with their fancy horse and their strong horse. And everyone's eyeing each other down. And it was a lot of fun to go to those competitions.
And, there was a lot of really hack stuff that we would see. And we always, got a chuckle out of the things that we found that people had done.
So much of what we learned and the rate at which we learned was accelerated by seeing what others had done and what worked and what didn't. So a lot of what, we integrated in the evolution of the Concept Z at Berkeley and then going forward and more importantly into the CHEETAH are a lot of other people's ideas, to be fair.
There were some other schools that had dominant teams. I remember Cal Poly San Luis Obispo having some good entries. We showed up to Sacramento State, and at that time, the big rival was John's older brother, Tony, from Chico State. And he goes, "How many bikes did you bring?" And I said, "We brought our one bike, the Concept Z." He goes, "Well, we brought two. We brought the Cafe and the Cafe Lele." I'm like, I didn't know you could bring two bikes.
I felt like they had really kind of dialed in the craftsmanship aspect to it. Their stuff was very clean, very well, executed. There wasn't a lot of hack stuff on their vehicles, but it just seemed like wasn't necessarily ideal in a lot of other ways. It was almost like they had kind of fixated on their particular design direction, but did a really good job executing it.
We could see where their design was deficient. Like they had difficulties with their actual position for their rider on their vehicle, and we looked at that and said, that's the position that we want our rider to get in. It was optimized more for aero efficiency and less for ergonomic efficiency. And they were very successful with it because of their execution. And they had tested, extensively. And so they weren't subject to maybe all of the surprises and mechanical failures. Like that was the thing about our first year when we went to Sacramento State. We had a lot of failure, but it was a lot of failure out of trying things and doing things that were new for us.
87 was the first year that we had developed and built our two-wheeled vehicle. As usual, we were working late into the night, every night leading up to the competition. When we got there, it wasn't done. We were like actually working on the bike through the middle of the night, pulling an all-nighter, to get it ready.
We encountered obstacles and we weren't prepared to go to Sacramento State in terms of having our vehicle not even tested, I should say, but barely even assembled.
Looking back, we're throwing cyclists in there saying, try to break a record, try to go 60 miles an hour in a vehicle that was basically not always really well tested and not always really well built.
The middle of the road race when we were doing extremely well, the handlebars came off.
I'm actually surprised that people didn't get more injured than they did, because you're really putting people out there like literally in untested equipment, but you were learning. This whole time you were gaining information and learning, and you'd go back and you'd be, all right, let's get ready for next year because we want to go back and we want to beat those guys. At Berkeley, we had a UC Berkeley cycling team, and we had one of the guys that was on the cycling team was named Matt Radovan, and he was actually a pretty strong cyclist. He was a mechanical engineer.
Actually, Radovan was not a mechanical engineer. He was a civil engineer.
He was in naval architecture is what his major was.
One of the things about the competition, the collegiate competition, is that you had to use riders that were in the engineering school. So to find somebody who's actually a strong cyclist and is also in the engineering school was a big challenge. And so Matt Radovan was the solution for us.
I think the cyclist has to be pretty fit to do well. But the bike, the aerodynamics would help out a lot. So if you had good aerodynamics, you could overcome some of the athletic shortcomings.
It's kind of a 50%, 50-50 scenario. It's a blend of man and machine, if you will.
If you want to break the world speed record, though, you need a very good cyclist. So in 1988, we were at Sacramento State, and we didn't do so well. But in 1989, we made a comeback. There are three parts to the ASME competition. You had the report and the design competition, which was the first day. The second day was the speed component, where you actually get out and you see how fast you can get the actual vehicle moving. And there's multiple runs. The third day then is a road race with multiple riders. So each of those 3 competitions then are added up for a cumulative score for the overall winner. We got first place in the design competition. James did an excellent job doing the presentation, and we won. So the report, along with the presentation, showed that Cal Berkeley actually had arrived. So the second day of the competition, which was the speed competition, this year they held it on a velodrome, which was a cycling track. And we actually placed, I believe, first or second overall in the speed competition. So all of a sudden, like, all of our design effort and the speed that we had designed the bike for started to pay off. I was really proud of the team and what we had accomplished. We finally had made it to the top. We were going into that third day, the final competition, clearly in a position to win the overall competition, which after many years of investment against all the other teams was super important for Cal Berkeley. And in that final day, that final race, we got hit by some side wind and we crashed, but we were way out in front. So finally, all that work we had put into it over the several years building the HPV was starting to pay off. There were probably 20 people that were involved in HPV, and basically at the end, it was 3 of us trying to break the world record. So we took all that technology of the 20 guys, like, we're going to do this. We were possessed. I mean, it was, once you invest in something, you're like, I got to make this work.
The goal of breaking the world speed record for human powered was always on all of our minds. It was kind of a pinnacle of achievement that we were interested in getting to. It was a collegiate competition for us in the beginning. And I think we were pretty realistic, that we weren't going to be breaking world records with collegiate athletes at collegiate competitions.
The world speed record was the thing. We weren't in a situation realistically where we were going to do that at a collegiate level with our vehicle, and knowing that there are so many other elements that go into it in terms of organization, location, execution, and support in many different ways to make that happen.
We had established a lot of expertise in the human powered vehicle, like knowledge base, and we said if we turn the handle one more time, we can break the record. So I think everybody was very confident that we could do it. We just needed the funding and we needed the opportunity. Someone say, yeah, we're gonna sponsor you and endorse you. But we had the confidence from going through Cal Berkeley and the years of competition to move forward.
I would say that, the opportunity to be involved in the collegiate competition really enhanced the education at Berkeley, to actually get some real world hands-on engineering experience working in a team. It was a great experience and it served me well over, my entire career in life. And, the transition into building the CHEETAH, the sort of taking a swing at something that's unlikely was just total gravy on top of it.
During that time, you're building all your tools, you're getting all this technical knowledge. But the thing that's missing in almost all of these colleges' experiences that comes from something like this is collaboration. So the big component that you get out of doing this project is working with other people and bouncing ideas off of other people and working cooperatively and coming together in a team setting. So that's not something that typically happens just by going to class every day and coming home and doing your homework.
If you just plan on school, you're a consumer of knowledge. You have to find your passions to apply it. And if you don't pursue your passions in life, you really can't really find true success. So the schooling was the backdrop. The education was the backdrop. The critical thinking skills were the backdrop. The bike project, the human-powered vehicle, the record, that's where it actually kind of resulted in something of importance. Because the degree is one thing you can hang on the wall, but hanging actually a poster of the bike you built is more important.